So now I'd like you to turn to Worksheet 8, which is also labeled Notes. I'd like us to look at the pH of a weak acid solution. We did a strong acid solution. Now we're going to look at a weak acid solution, and these steps are going to become so much more important. We are going to calculate the pH of a 0.5 molar aqueous solution of formic acid. This is the acid that you find in red ants. The formula is HCOOH, and the Ka is given to us at 1.77 times 10 to the minus fourth. So we need to list the major species. As always, water is there, but really what we're looking at is the formic acid. We need to choose the species that can produce H+, and write balanced equations for the reactions producing H+. Again, we're starting simple. There's just one thing. It's the only thing producing H+. Now, when you write this, it is this final H is the one that comes off. It's not this first H. However, I wouldn't expect you to necessarily know that, and it would be okay if you accidentally pulled off the wrong H in this case, since I know we're very, very used to pulling the first hydrogen off. But just because I know some more things, I know that it is the final hydrogen. But I don't want you to be concerned by that. Step 3 says, using the values of the equilibrium constants for the reactions you have written, decide which equilibrium will dominate in producing H+. Well, there's not much decision to make here because there is only one thing. And so we have our Ka, which is 1.77 times 10 to the minus fourth. Step 4 has us write the Ka. And this is going to be important for every problem we do. We're going to want to write our balanced equation, and then we're going to want to write our K. And I'm actually going to go back so that we can see this equation right up here at the very top. So our Ka is equal to the concentration of the products, H+, times HCOO minus, over the concentration of the reactants. We can go ahead and set that equal to the number, because we're going to need that as well. And so this problem continues on to the next page. And by doing so, this is going to be the most important and new step for all of this. So step 5 says to list the initial change in final concentrations of the species participating in the dominant equilibrium. In other words, make an ICE chart. Okay? And ICE stands for initial change, and we use equilibrium, which gives us the E, but it is the final concentration, or it is the equilibrium concentration. So we refer to it as an ICE chart. And you're going to set this up by using that equation that you wrote. So you wrote HCOOH, that's why that equation is so important, becomes H plus HCOO minus, and right down the side we're going to list I, C, E for the ICE chart. Well, what concentration of formic acid did I start out with? When I started the reaction, I put 0.500 molar formic acid into water. Initially, I have none of this. Now, in a strong acid, all of this breaks apart into this and to this. So I would end up with 0 formic acid, and I would end up with 0.5 and 0.5. But in a weak acid, that's not the case. A strong acid completely dissociates. But a weak acid, which is 99% of what we're going to be dealing with, in a weak acid, only some of these are going to break apart. The question is, how many of them are going to break apart? Well, we don't know. We have no idea. And so that makes this problem kind of hard, but in some ways kind of easy. When we don't know, when we need a variable, well, when we don't know something, we call it x. So my change, this is going to go down by x. This is going to increase by x. So at equilibrium, I have 0.500 minus x. I'm just following this problem down. And I have 0 plus x, which I can just fill in as x, because 0 plus x would be x. I'm going to then take that information and plug it in to my equilibrium expression. So I'm going to take my Ka value. So I have Ka, and I'm just recopying it here. I know you already have it, but I want you to see where everything is getting plugged in on one page. So you wouldn't have to write this again here because I know you have it earlier. But we're going to take the 1.77 times 10 to the minus 4th, and that's equal to, well, what do I have in this column at equilibrium? Well, I have x. What do I have here? Well, I have x. And what do I have here? Well, I have 0.5 minus x. Well, if we were to solve this all out and simplify it, we would see that this times this would give us a number plus a value with x plus an x squared. So essentially, we've just solved for and gotten a quadratic equation, which means that every acid-base problem requires us to use the quadratic equation. A squared plus b squared equals, I'm sorry, that's Pythagorean theorem. The minus b plus or minus the square root of, and all of that stuff. But we're going to make it easier. So in chemistry, we can do some things that you can't do in math. And so in chemistry, we can go ahead and we can just say that that x is probably not all that important. And we're just going to take it out of our problem and not use it. We're just going to eliminate the x. Now, there's some rules about what x's we can eliminate. We can't eliminate an x that's all by itself, meaning there's no other number with it. That we just can't do. But when there's an x subtracted from a number, we can eliminate it as long as it fits in our criteria. So this makes our problem much easier to solve. So let's solve for it. 1.77 times 10 to the minus 4 is equal to x times x over 0.5. No more nasty quadratic. I just end up with, I multiply those two. I take the square root, and I end up with x is equal to 0.00941 molar. And x is my hydrogen ion concentration. If I look back here, x is what was equal to my hydrogen ion concentration. So now I've solved for my hydrogen ion. If I'm going to eliminate that x that's subtracted from something, I have to use something called the 5% rule. So I need to see whether that's valid. I need to take 5% of original concentration. So I'm going to take 0.05, which is 5%, times the original concentration of 0.5 molar, and I get 0.025 m. That number, that 0.025 molar, must be greater than the 0.00941 molar, which it is. So we need to write something like 5% rule OK, because that to me indicates that you understand and you know and you checked and you showed me that the 5% rule is valid. Which means that that answer, this does have some obviously break apart, but so little so that in the realm of significant figures, it's not that important. So we knew that our x was equal to H+, that's what it was when we solved, and we got 0.00941 molar, which means my pH, which is the negative log of that number, the negative log of 0.00941, my pH is then equal to 2.026. I know that's a lot to take in, and that's a new type of problem, but there are other practice ones that we're going to do in class, and so when you work in your groups, you'll be able to work through these steps and ask questions to be able to practice using these steps to solve this type of problem.